So the partition function was defined as in the previous section as the molecular partition function as the sum over energy levels, and we wrote it at e to the power minus beta epsilon I. Now this I, remember, we said that we have some let's say energy levels, and each energy level in this case has one particular state, meaning this sum is actually over the energy states. However, you may encounter a situation where suppose you have some degeneracy for the states, and then we have to be very careful. So then what we do is that we take simply this number e to the power minus beta epsilon I, the Boltzmann factor, and then multiply it by the degeneracy of that state, and then take the sum over all the energy levels. So in this case, actually it is the sum over levels. So each level I has GI fold degenerate. In the earlier case, actually we are taking sum over states. So we have to be very careful when whether this I corresponds to levels or I corresponds to states. Let me give you an example. So for particle in 1D box, we know that or 3D box, and suppose think about this, this is an cubic box. So what we have, the total energy there, I am using epsilon notation. Let me just use the epsilon notation here. So that is given by n square h square by 8 ml square, but in this case actually it is it will have three quantum numbers, nx square plus ny square plus nz square h square by 8 ml square, where L is the length of the box and m is the mass of the particle. Now the interesting thing is that suppose we say that we just take an energy levels, let's say 6 h square by 8 ml square. Now this energy level is how many states are there at this energy level. We can see that there are three states. Why? Because I can choose nx to be equal to 1, ny to be equal to 1, and nz to be equal to 2. That will satisfy this energy level, because 1 square plus 1 square plus 2 square is 6. I could have chosen nx to be 2, ny to be 1, nz to be 1, or nx to be 1, ny to be 2, nz to be 1. So I see that there are basically three states: 1, 1, 2, 2, 1, 1, and 1, 2, 1. But all these three states corresponds to the same energy. So each energy level or this particular energy level is threefold degenerate. So in order to calculate that, the GI will be 3. So that way you have to be very careful that whether we are taking it the sum over states or sum over the levels. Also, one important thing for the Boltzmann factor is that if you remember the way we wrote it, the probability, like we wrote it as ni by n, and that is basically equal to the e to the power minus beta epsilon I divided by the q, where q is the molecular partition function. So we wrote it as ni divided by capital N, or the probability is nothing but e to the power minus beta epsilon I by q. That's another way of writing it. Now suppose I have two energy levels. I have many energy levels, and I'm just talking about the two particular energy levels, and if their number of particles in these energy levels are ni and nj, then we can also predict their ratios. Ni by nj will be nothing but, you can see here that I can actually directly use this formula for the probability, and you can easily see that this q actually gets cancelled out. So I'll have e to the power minus beta epsilon I divided by e to the power minus beta epsilon j, which together we could write it as e to the power minus beta epsilon I minus epsilon j. Now you see that the relative population, which is the ratio of the population, is dependent on the difference in the energy levels, and that's a very interesting thing, because you can actually now think in terms of the real energies. For example, if I have translational energy levels, And we know that the translational energy levels will, according to the particle in a box model, will go like this. It goes as 1 by n squared. So as we increase in energy, the gap between the energies decrease. Now what we say is that at room temperature, consider these things, you will find that beta is nothing but 1 over kBt. So I could write it as e to the power minus epsilon I minus epsilon j divided by kBt. Now let's say at 300 Kelvin temperature, you can actually calculate for a particle in a box model that what is this energy gap with respect to the thermal energy, which is kBt, and you will find that its energy gap is extremely small. So you will see that the difference in the population won't be much, in a sense, or in other words, there will be many energy levels which will be populated, the many translational energy levels which will be populated. Similar thing will also happen for the rotational energy levels, and where we have some energy levels like this, and then the energy levels are also degenerate. We'll also see that for rotation also many energy levels will be populated at room temperature. But for vibrational energy levels, the energy gap is pretty big, and you will see that you can actually calculate this particular ratio. If I have the total number of molecules, let's say, or you do not need to know the total number of molecules, you can just calculate the fraction, and you will figure out that for vibrational, but it of course depends on which vibration you are talking about, what is the exact energy level difference between them, whether it's a low frequency vibration or high frequency vibration. But for any general calculation, let's say if you take 1000 wave number vibration learn frequency, you can actually convert it into energy scale in terms of joule or something like that, and then you can actually calculate. You can take the temperature to be 300 Kelvin, and you can calculate that if I have let's say this is the 0 point energy of vibration, and this is the first vibrational energy level, V equal to 0 and V equal to 1. So how many molecules are there in or relative to the total number of molecules, what is the fraction, that you can easily calculate. And then you will figure out, you can also, by fraction I mean this number also you can calculate for individual energy levels. You can also calculate the ratios. But if you calculate that, then you will see that more than 99.99% molecules are residing only in the 0 energy level. So vibrational energy levels at room temperature is very much behaves like a discrete. So you see a quantum mechanical effect from that. But usually for translational and rotational partition function, we'll treat them as if they are continuous. That is the meaning of this continuous distribution in the Boltzmann sense, that if you talk about the translational or rotational, you do not really see the quantum mechanical effect at room temperature, because many energy levels are populated, and because kBt is much higher compared to the energy levels. However, for vibrational or electronic energy levels will be far more separated. You see only the ground vibrational state is predominantly populated. For electronic, it is you will see exclusively the electronic ground state is populated, because it is very difficult to thermally activate the second electronic states. Although there are examples of thermally activating the energy levels, electronic energy levels. But let's not go into those details. Now let us try to calculate this partition function. First thing first, we are going to calculate what is the translational partition function. Now, what is the translational energy levels? If I take let's say the energy level, particle in a box energy level for a 1D box, let's say particle in 1D box. So for that, the energy level is given by I have only one quantum number, n square h square. H is the Planck constant, divided by, it's not h bar, it's n square h square. We could write it in terms of h bar also, by 8ml square. And then I'm denoting the energy level with an suffix n. And for a, so then I can just use the sum over state formulation, because in this case actually there is no degeneracy. So I am taking sum over n. The index I is arbitrary because usually I am denoting it in terms of the quantum number, and it is nothing but e to the power minus beta epsilon n, and which is nothing but if I take the sum, it is nothing but e to the power minus, so it will be n square h square by 8 ml square, so it will be n square times a constant which is nothing but beta h square by 8 ml square, something like that. Now since as I said that compared with the beta or 1 over kBt, so at room temperature the energy levels are far more closed or closely packed, so then I can think that instead of the sum I can actually integrate this quantity, and then I will have e to the power minus n square into some constant. Let me just write this constant as say a, and then I'm integrating it, and the variable is now n, and where actually the energy levels are going from 0 to infinity. So although it's a truly speaking it's a discrete energy level and it will take the values of 0, 1, 2, 3, but since at room temperature the many translational states are populated and the space between the levels are much less, so you can think that it is as if it is a continuous distribution. Now there is one interesting thing here, that if you remember that for particle in a box I'll have the energy levels like this, which is ever increasing, n equal to 1, 2, 3, 4, something like that. Now the question is whether this partition function we are measuring with respect to the ground state or not. So if we do with respect to the ground state, so for the ground state the energy level is n is equal to 1, so the energy level will be the energy will be 8 ml h square by 8 ml square. So all the energies with respect to the ground state, that if I had written it, then I should write it as n square minus 1 into h square by 8 ml squared, and then we basically write this thing as remember that n actually goes from 1 to infinity in our case, but it's a discrete sum again, but then we are writing n equal to 0 and the denominator. But if we do this transformation that we are measuring everything with respect to n equal to 1, then actually I could write the lower limit as n minus 1 and the lower limit will be 1 minus 1, which is 0, and then this thing, instead of the integration writing as this, I should have written it as e to the power minus n square minus 1 into a into dn, where n is going from 0 to infinity. Up to this level actually I have n equal to actually 1 to infinity, but then if we write it in this way, then the next stage we say that okay fine, e to the power minus n, since n is very large, so I can actually approximate it as n squared, and there is a here, something like this. But we are not actually following that notation. Rather we are saying that okay fine, the n is going from 1 to infinity, but I can actually add n from 0 to infinity to because it's adding nothing. If I just add n equal to 0 in the sum, it will of course add some number to the partition function, but if I start from 0, the energy level is not changing. I mean there is no energy at corresponding to 0. So you could use either way. So remember that we used one of this notation, that approximation notation for going from summation to integration, and the second one I am writing here that changing the limit from 1 to 0. On the other convention, I think Atkins has used this convention that he was measuring energies with respect to the ground state. So in that case I write it as n square minus 1, and automatically the limit is from 0 to infinity, and but then you approximate it as n square minus 1 as n square. Now, how do you calculate, how do you evaluate this integral? So, this is a very straightforward integral, but we can actually use the gamma function integral for this. What is a gamma function? The gamma function is defined as, so you can use standard integrals for this, and the gamma function is defined as like this. If I have an integral like this, e to the x to the power n minus 1 e to the power minus ax dx, that is equivalent to gamma n by a to the power n, where gamma n is nothing but n minus 1 factorial, and if I have something like gamma half, it will be root pi. So, for example, if I have say gamma 3, it will be 2 into, so n minus 1 factorial is 2 factorial. We can actually write it as 2 gamma 2. It will be basically 2 times 1 times gamma 1, and gamma 1 is nothing but 1 because gamma 1 is 0 factorial. So, that will be 2. So, this is how we will evaluate it. If I have something like say gamma 5 by 2, so it will be 3 by 2 gamma half, and gamma half is root pi, so it will be 3 by 2 root pi. So, in that way, we will just evaluate the gamma function. Now, let us see the mathematical form here. It is e to the power minus x square a into dx. So, I have to write it in terms of the gamma function. It is something like e to the power a x square dx. I have just written I'm just writing x in place of n, but this is exactly the same. Now, how do you write it in terms of gamma function? Let's see that here I have actually x square. So, and here if I have dx, then I have e to the power minus ax. X is the variable. But now, can I actually change it to x square variable? So, that I can easily do. So, I will just write it as d of x square. Maybe I can actually use one more step so that you understand more clearly. So, my final goal is that I will just write it as d of x square. Now, d of x square is what? It is 2x dx. Now, so if I write it like this, 2x dx, in the next line I will write it as d of x square, but this is an extra 2x dx. So, I have to write it like 1 over 2x also I have to introduce, 1 over 2x e to the power minus ax square, that is the integral. So, I have just introduced divided and multiplied the entire thing by 2x. Now, let's see how I can actually write this 2x. So, it is nothing but half I can take out of the integration, it is just a constant. Now, it is x to the power minus 1. Now, x to the power minus 1 is x square to the power minus half, and minus half I can write it as 1 minus half. So, you see 1 minus half is minus half, and x square to the power minus half is x to the power minus 1, which is 1 over x, and then I have e to the power minus ax square. Now, you see the beauty. Now, it actually matches with the gamma function. I can actually switch now the variable, write x square as y. So, it will be y to the power n minus 1 e to the power minus ay dy, that is a gamma function. So, instead of the variable x, it is now x square, and what is n here? N is basically 1. Sorry, I made a mistake here. So, it is n minus 1. So, it will be half minus 1. That way I have to write it here. So, since I had minus half, I have to write it as half minus 1. So, this integral is nothing but gamma n by a to the power n, and which is nothing but gamma half by a to the power half. Now, gamma half is root pi, and what is a? A is we approximated a to be this entire thing, beta h square by 8 ml square. So, beta is 1 over kbt, you can just write it, h square divided by 8 ml square into kbt. raised to the power half. So, and then remember that there was a half here, so I have to also use this half here. There is a half here. So this is the translational partition function. Let me actually write it in a more compact form. So this 8, square root of 8, it will be in the numerator. Square root of 8, that we could write it as 4 into 2, so that 4 comes out. So that cancels with the 2 in the denominator. So this 2 gets cancelled with that square root of 4. So I'll be left with 2, and I have a pi, and then all these things m kbt divided by 8 square, entire thing to the power half, and into L. So this L square I'm taking out. So this is the formula for translational partition function. 2 pi m kbt into to the power half into L divided by h bar squared. Now if you have the particle in a 3D box, let me just write it. So Q translational for 1D we got it as like this, but remember that if I have a particle in a 3D box, the energy levels are basically additive, because the total energy level, instead of writing it as En, the summation will be, now I'll have 3 energy levels. I'll have Enx plus Eny plus Enz. And how the partition function will go for this. So then you can easily think that the partition function will be like summation over Nx, Ny and Nz. Now it is basically e to the power minus beta into energy. Now energy is additive, so it is basically Nx plus Ny plus Nz, and then actually this is a triple sum over Nx, Ny and Nz. Now you see that I can actually, since it's an exponential to the power something, which is addition of 3 terms, I could actually write it as the multiplication of the exponentials. So and then I'll have the triple sum e to the power minus beta epsilon nx times e to the power minus beta epsilon ny times e to the power minus beta epsilon nz, and there is a triple sum, so I can actually evaluate them separately. So it will be e to the power minus beta epsilon nx times the second term ny e to the power minus beta epsilon ny, and similarly I'll also have nz thing, e to the power minus beta epsilon nz. So now you see that these are basically translational partition function for 1D, but for nx, for ny and for nz. So we see that since the energies are additive, so the partition functions, since it goes as exponential to the power energy where the energies are additive, will get always the multiplication of the partition function. So this is the 3D partition function, and each of them will give you the same value, 2 pi m kbt divided by h square raised to the power half into L. And then what we will have here is something like 2 pi m kbt raised to divided by h square to the power 3 by 2 into Lx, where Lx is the length along x. Similarly, this will be half. This factor will be 1 over 2, and similarly the same factor into Ly, into the same factor into Lz. So together what we see here, so this Lx into Ly into Lz is, if it is a rectangular box, So that is nothing but the volume of your system. So what we usually do, you usually calculate the translational partition function per unit volume, and then you say that these things basically gets multiplied. So we'll get translational partition function per unit volume as 2 pi m kbt divided by h square raised to the power 3 by 2. So this is the total translational partition function for a molecule. Now we will see what are basically the rotational partition function, and eventually we will see what are the vibrational partition function.